Hello there, I'm the Code Dog, and today I want to talk to you about parallelism in Python. I've found myself making use of parallelism quite a bit lately, and quickly realized that there's quite a lot to it. In fact, there's at least 4 different modules in Python that are all intended to provide parallelism. I'd like to go over all of them with you, but that isn't really feasible to do all at once. As such, this will serve as the first in a series where I go over things like threads, multiprocessing, the GIL, and other topics related to parallelism in Python. Parallelism in general, meaning not just exclusive to Python, is typically handled by something called a thread. A thread can be thought of as a more lightweight version of a process that runs within your program. So the same way that you can have multiple programs running at once when you use the computer, like Chrome, Discord, Steam, etc., you can have multiple threads running at once inside of your program. The most common example of this in everyday life would be just about any GUI application. Typically, you can do things like press a button that will kick off a task, and the application will remain responsive to clicks or other inputs. Another use case, and the one I will be going over today, is using threads to speed up total processing time. The type of application in this case wouldn't necessarily be a GUI, but instead is perhaps a command line tool that needs to process data or maybe even to automate a series of tasks. The idea is that if there are some steps in the program that aren't dependent on each other's output, then there isn't really need for the program to sit around waiting for one step to complete before it starts the next step. Overall, the result is that the total runtime can be reduced to just the time it takes to complete the longest of the steps, plus the overhead time associated with initializing the threads. Now, before I go on, I'd like to note a caveat to what I've just said, lest I anger the Python nerds, and that is that Python doesn't really allow for true parallelism with threads. The reason for this is because of something called the global interpreter lock, or GIL for short. I won't go into too much detail on that in this video, but essentially what it means is that if the functions we want to run in a thread are what is known as CPU bound, then the code will take just as long or longer as it would have if we had called all of the functions serially instead of in parallel. But for functions that are known as IO bound, then we can in fact achieve improved performance with parallelism. For those unfamiliar with the terminology, CPU-bound code is code that would take longer or shorter to run depending on how powerful your CPU is. IO-bound, on the other hand, is code that when run needs to wait on input from something running outside of the program. In other words, it is code that would take longer or shorter to run depending on things like network speed, disk read-write speed, and so forth. If you'd like to learn more about all of that, I do plan on making a video about it at some point, but in the meantime, feel free to check out the links down in the description below. At this point, I'd like to introduce this simple function. Its purpose is to download a file at a specific URL, search for instances of the word the in the file, and return the total count. If the HTTP request fails, print the exception and return -1 to indicate that something went wrong. Note that this function is both IO bound due to the network requests for the file, and CPU bound due to the processing it does on the file. If we run the function with one URL, we can see it takes on the order of a few hundred milliseconds to complete. It's not much of a stretch to imagine wanting to use this functionality on multiple URLs and then doing something with all of the results. Either displaying them or averaging them comes to mind. Without threading, this would just be a for loop that iterates over a list of input URLs, runs the function on each one, and then appends the result into a list which can be aggregated by displaying it or averaging it. Running it on this set of URLs takes about 10 to 15 seconds. That's not an unreasonable amount of time, but it also wouldn't be unreasonable to ask for a little bit better performance, especially if this is expected to run on many more URLs. It's reasonable to suspect that threading would give us such improvements as our function contains a decent amount of IO-bound operations, so let's give that a shot. First, we will need to import the thread class from the threading module. In order to threadify our function call, we simply need to pass the function into the thread constructor. Since our function takes in an argument, we need to pass that in as well by using the args keyword like so. To start the thread, simply call the start method for our thread object. Running the code as is, we get a runtime on the order of milliseconds. That's on the order of 1,000 times faster than when we ran it before. If you're even a little suspicious of what I'm claiming right now, you'd be 100% justified. You see, we forgot an important step, which is to tell the program to wait for the threads to complete and gather the results. The time we just saw was actually just the time it took to iterate over the URLs and kick off all the threads. Those threads will run, but will be run in the background of our program until we bring them back into the foreground with the thread.join method. Of course, we can't do this inside of the for loop because that would just cause us to wait for that thread to finish before we have the chance to kick off the next thread, effectively producing the same performance we would see serially, probably worse due to the overhead of creating the threads. Instead, we must put each kicked off thread into a list and then iterate over all of the threads, calling the join method as we do so. Okay, that was definitely an improvement, but what are all of those nones? Well, after some Googling, I am reminded that the default thread class doesn't actually provide a way to access the return values from our function. I'm not going to lie, that's pretty frustrating. The silver lining is that when I am done here, it's going to be easy to convince you guys to use the futures module whenever I get around to going over that. For now, what exactly can we do? Well, one idea would be to modify our function to take in a mutable object like a list that will serve as a repo for our results. Awesome, we've got results. This would be acceptable if we didn't care about the order. For example, if our goal was to just get the average, we could simply do this. But what if we wanted the results to be associated with each of their URLs like so? If we do this for our threaded results, we see they don't match up. What's happening is that our results aren't in the order in which we started the threads, which matches the order of the URL list, but instead is in the order in which the threads finished, since whichever thread finishes first will append to the list first. To get a results list that corresponds to the URL list, instead of appending to a repo list, we can instead insert into one that is pre-allocated. This requires one more modification to our function, and another modification to our for loop. The result is a properly ordered set of answers. So, after all of that, just how much of an actual speed boost did we get? Was it worth it? Well, since the major bottleneck is network speed, which can be volatile, it's actually kind of difficult to accurately profile the performance of both approaches. That being said, it's easy to see that running with threads provides a performance boost of at least an order of magnitude. And that's all I had for this topic. If you like what you saw, I'd appreciate it if you give this a thumbs up for the algorithm. If you have any questions, definitely let me know down in the comments, and I will do my best to answer them. The comments aren't the best medium for such discussion, but I can certainly try.